Alright, good morning. Let's continue with our top interview 150 LeetCode problems. Yesterday we did the longest substring without repeating characters, which is a medium, already pretty difficult. Now the next one is a hard one in sliding window. So I'm not sure I'll be able to pull this off, so we shall see. We will try for an hour. If I cannot even have an approach, then we will give up and look at top solutions. Alright, let's read the question and stop the timer. You're given a string and an array of strings. All the strings of words are of the same length, okay? A concatenated substring in S. It's a substring that contains all the strings of any permutation of words concatenated. Okay. Concatenated substring. Okay, even though it's called substring, but it actually contains all the strings of any permutation. All the strings of any permutation of words concatenated. So in this case, it will all have the same length, 6. So I'm not quite sure what is called a substring. Okay. Anyways, so it's supposed to contain all the strings of any permutation. So there are only 6 cases because we have 3 different strings here. So permutations of that. Return the starting indices of all the concatenated substrings in S. Starting indices. Starting indices. Input is bar full, the full bar man. Words is full bar. Okay, I don't understand the question. Okay. You're given a string S and an array of strings, same length. A concatenated substring in S is a substring that contains. Oh, I see. Now I understand. Okay. So we have this string S and we are looking at the substring. Okay. So it is a substring here that contains all the strings of any permutation of this. So when we are given words full bar, the only permutations we have are full bar and bar full. So we have bar full and full bar, both of them here. So that's the concatenated substring in S, bar full and full bar. And we want indices, starting indices, which is 0 and 9. Okay, now I understand. Oh, that's an interesting take. So the length has to be 6. So when we're checking, we check the substring that has length 6 at index 0, that is bar full, and that is a valid concatenation. And then when we're at 9, that is also a valid concatenation. Okay, word, good, 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 best word. Word, good, best word. Word, good, best word. Good. Okay. Next one. Bar, full, full bar, the full bar man. Bar, full, the. Bar, full, the. Bar, the full. The full bar. Those all work. All lower English letters. Okay, so we understand the question now. So brute force idea, since the explanation is kind of leading us that way, is that we will first, okay, the length has to be 6. So then we check at index 0, what is that substring that has length 6? Okay, that's bar full. Is that a valid concatenation? Which means we also need to first have a list of valid concatenation. And I'm guessing, I'm suspecting that if we do brute force, the time efficiency is not super good. So it will probably run into time limit exceeded. Oh, and let's not forget that we are supposed to solve this with a sliding window, which is not given as a hint here, but it's categorized as one of the sliding window problems. Interesting, because otherwise I wouldn't even thought of sliding window. I definitely need more practice in sliding window problems. Alright, let's now rethink in terms of the sliding window technique. Okay, so we know the length of our window, it's always gonna be 6. We start from this window. Do we have a more efficient way of checking whether that substring is a valid concatenation? We could, of course, start with a whole list of all valid concatenation. So in the case of 4 words in this words list, the number of valid concatenations, the number of permutations would be 4 times 3 times 2 times 1, the factorial of 4, and words length at 5,000. I'm almost kind of inclined to just try out the brute force first to see what's the time spent there. If it passes, if it's the time limit that is not working. What are some other things that we can consider? So I'm thinking in this case, since the length here are of 3, so when we're looking at bar full, if that doesn't work, the next one we should look at is index plus 3. because it wouldn't make sense to check from this index. Or would it? Oh wait, it would. Yes, it would make sense if this is not valid. But if this is valid, then we know that this is of length 3. And do we still need to check from the next index, or can we skip 2 in that case? We cannot skip. Or wait, can we skip or not? What if we had something like powerful? Could we have something like ARF? Oh. Not sure. Not sure if that is possible to have a valid substring here and then also a valid substring starting from the next index. We'll have to spend more time thinking about that. Okay, for now, let's skip that. So, the sliding window. Let's try with this more complicated example. So, we have this window, bar full. It looks like the answers are all starting somewhere at multiple of the length here, so multiples of 3, 6, 9, 12. It kind of looks like it's not possible to actually start at the other indices. I would very much like to have some kind of mathematical proof on that instead of just an intuition. Well, I guess in this case it does work. If we had a string like this, 8 A's, and then the words are A, then we just need to find all the 6 A's, which means that works. Oh, and that works, and that works. So in this specific case, that does work. So I don't know if it can be generalize to more common cases might just not work. But now I at least know that this does exist. Okay. Alright, I cannot think of any other ideas right now, so let's do this brute force first. Let's have a list of all the permutations, and then we will go through this string S and check if any part of it is a valid substring. Alright, so we want iter_tools from iter_tools. So Python iter_tools permutations. So that gives us the list of all the permutations from a list directly. Okay, so we have this input GEEK, and we want the permutations of that. That will give us time complexity factorial. So that gives us the factorial number of permutations. Okay. We want to know what this returns. I want to see what this returns. I want to know the type that it's returning. Okay. Oh. It's only 5 a.m. by the way. I woke up at 4, so permutations. I forgot permutations of permutations. What do we name this? First, permutations. Permutations of words. I want to see what this returns. Print. Returns an iterable. Okay, it returns an iterable, and then we want to put those iterables into a string. Okay, that's what we want. So strings, we want a list, and now for all the permutations, we want to put that P, which will give us a list in, and we want to put them into a string. Can we do something like a join? Let's see if that works. So join this iterable into a string, and then we want to append that. So now we have that list of all the concatenations. I want to see if this works first. What do we have? Okay. Okay, so that one is okay, it is returning what we are expecting. That's good. All right, so we have those concatenated strings, and now for I in range length of s, for each substring of that specific length that we're looking for, so the length will be 9. For each of those 9 length substrings, we want to check if it is in one of those concatenations. So how do we do that? Can we get the substring from S? So how do we do that in Python? Can we do something like, so what is the length that we want? The length would be the number of words, in this case 3 words, times the length of each word. So that's the length we're looking for. This current substring we want to check is gonna be S. That starts from I. I'm not sure if this is the correct syntax. Let's check. So Python substring with index. Okay, let's try that. From I to I plus length. I'm not sure if that's exclusive or inclusive. So 6 to 11, that gives us 5. Okay, seems like that's inclusive. So that's the substring, and we also need a final result array list. If this substring is inside this strings, we need better names. What do we call this? Well, this is all potential substrings, all the concatenations. If it is in there, then we want to append the current starting index. Okay, let's try that. Unsupported. Oh. Huh. Okay. Not sure if that's the problem, but let's see. Okay, what is the type here? Oh my god. Of course. We want to get the length of that, not that. Okay, what's happening here? Why do we have these outputs? Am I printing anything? Hmm. Oh, right. Interesting. And I substring. And I'm wondering why it's not giving the correct substring. That is very interesting. And why isn't this incrementing? Okay, we are not doing something correct with this indexing thing. So and is incrementing, but the substring we are getting is not correct. Oh, is it because that we... Okay, let me check one sec. The full bar. So the full bar. Case 3. We should be going from 0 to 9. It should return bar full full. Why is it? Oh my god. It's because I have this. Okay. Really need to take care of this silly mistake. So I have rewritten the string s instead of using the original string s. Okay, let's can fix that. Interesting mistake. Okay, so at least those are working. Let's see. Exactly. Passed a lot of test cases, but memory limit exceeded. That's exactly what we were worried about. This brute force approach will exceed either... Well, I was thinking it would exceed the time, but now it's actually memory limit exceeded, not the time. Because I suppose there are too many permutations from this. So is that not the way to solve this? We cannot do the permutations? All right, let's see if we have another approach. So that's the brute force approach. Could we do something like this? So first we have this bar foo foo. Could we do something instead of writing out all the permutations and see if this is in that list? Could we do something like, okay, we have bar foo foo, let's check. Is bar in here? It is. Somehow we cross it out. Is foo in here? It is. We cross that foo out as well. Now we have another foo. Is that foo in there? No. So that failed, since the order doesn't matter. So that failed. Either we continue with the next index or we somehow... we need to continue with the next index, yes. And then we see, is arf in there? No. So words have at most 5,000 in... No. Oh yeah. Okay, 5,000 words at most. So each time we do this, though, it will have to go check. It has to go check if that is in words. Okay, we can put all the words in a dictionary, so the lookup is constant time instead of linear. Okay, all right, let's try that. I think this failed summation is saved here, so we are safe to remove this solution. Okay, so we want a dictionary. Can we make a dictionary of all these words? So these are gonna be the key. What is the value? We don't need values at the moment. Oh wait, we do need value because the words could be duplicated. It could be bar bar foo the. So in that case we have 2 bars in there. Okay, for each word in words, if a word is not in the dictionary, then we put that word in the dictionary and give it 1 because the frequency is currently 1. Otherwise, if it's already in the dictionary, then we can increment. So now we have this dictionary which has all the words and its frequency. So now we go through this, and what do? We check, see if it's in the dictionary. If it is, we decrement its frequency, and once frequency is 0, we can delete that from the dictionary. Or we keep it there and we have to check frequency every time. Okay, so let's try that. Except now we will have to do that for each potential subarray. So we tried that for this subarray, then we tried that for this subarray. That still seems very inefficient to rebuild that dictionary each time, which takes linear time. So building that dictionary takes linear time. Lookup takes constant time. How many lookups do we need? For each for each substring, we will need the number, exactly the number of words, that many lookups. And then we need to do this for this entire linear outer for loop that checks all the potential substrings, unless we could figure out some other way to save operations there. All right, let's write this first. So we have this dictionary, we put those words in the dictionary. Well, we don't actually need to rebuild the dictionary each time, we just need to reset it to the original dictionary each time. So how about we just copy a dictionary and use that copy dictionary. We still need to copy it. That's still linear. Yes, if we want to do a deep copy. Or wait, can we do a shallow copy? Oh, that's still linear. Okay. Okay, so we have this dictionary we can use the similar structure here. So we go through this, we find the end. Forgot about that. So that's the index, that's the end. Current substring is that one. And now we want to check each of those words in this current substring. Okay. So we just need the length of each word, because we're just checking like 3, 3, 3. So that's the length of each word in this words list. Okay, so that's the current substring we want to check, just this bar. And we want to do this for how many times? As many times as the length of word. For J in range, length of words. So we have 3 words, then that means we want to check 3 times. That's the length of this potential substring. So we want to check 3 times. And what do we do inside? We're checking 3 times. Okay, so that's the bigger outer loop that will give us where it starts. So it starts from I plus J times J times the length of those words. So first it starts from 0, so 0 and 0, then J should go to 1, so 0 plus 1 times 3, so 3, and then 2 times 3, 6. So it's checking 036 each time, and you want to go to this length each time. This plus length. Okay, start should be this. So that's the start of where we're checking, and then the length will always be the length of these words. So that's the current substring I want to check. Okay. Okay, that's where we want to build this dictionary. So now we have a dictionary for all the words. We build this dictionary. Okay. We have this dictionary now that has all the words. If this current substring bar is in the dictionary, then if it is in the dictionary, then we want to, okay, yeah, let's do deletion in the dictionary instead. Okay, so if it is in the dictionary, that means it's at least got frequency 1. So we can decrement with 1, and if it is not 0, then we can delete that. Okay, this could definitely be refactored, but this is the logic, so let's put it there very clearly for now. And I'm new to Python 3, so I wouldn't know the best way to refactor, so please let me know if you know. Alright, so if it is in the dictionary, then we decrement its frequency. If it's the last word, then we delete that from the dictionary. Otherwise, if it's not in the dictionary, so in this case, we have bar, we found it, we decrement frequency from 1 to 0, it's deleted. We found foo, same thing. Then we have foo is not in the dictionary, which means this is not a valid substring. What do? We can just break, because this is not valid. Then we break out of this, we try with the next one. And what if we succeed in finding this substring? Then we want to add that to the final result. So where do we do that? So we're looking at all the words, and they are all good. We haven't gone into break to the next one, so we've gone through all of these, and they are all found in the dictionary. What do we do then? Could we just do result append I? That's what I'm thinking. Okay, Can we try this? Wrong answers. Oh, interesting. What is happening here? Oh, I see. Okay, it breaks this for loop, but then it will just append the result. So what we need is that it breaks this for loop, and it also continues to the next I directly. Okay, else. Okay, this might be like a dumb way to do it, but let's say found is false. Okay, found is true. Found is true. And if we break here, that means we didn't find it. Found is not false. And if we found it, that's when we append it. Okay, at least it returns the correct result for case 1. Let's see. Interesting. Okay, word, good. So word, good. Words. Oh wait, we need this dictionary to be built here. Outside of this inner loop. In the inner loop, we're checking if all the words are in the dictionary. So the dictionary needs to be built outside of it. I don't know why I put that in there. Okay, very promising. Let's see. Oh my god, fingers crossed. It will not work. It's taking too long. Ooh, alright. Time limit exceeded on exactly one test case. We passed all except one because it's not optimal. Oh my god, this is that A example that I gave in the beginning. Interestingly. So in this case, time limit exceeded because so we have just a bunch of A in the dictionary. Well, I'm still pretty happy that we even got this far though, since this is a hard problem. Alright, so we have a bunch of A. So this dictionary will just have this A, then a big frequency number. And now since all these are of length 1, it means all these all these potential substrings, that's just length one character, checking that, and then we're decrementing from the dictionary. Is there any way we could improve on this, considering this test case of just same letters? Okay, so what if dictionary only has one key? That means we only have that same letter in the words list, and I mean, I could write a little code that covers this special case, which will check it and it will pass because it will be more efficient, but that's not really solving it though, isn't it? I'm still curious to just do that and see if this solution is really slow, because then we know this is still not the right approach anyways. So how about we try that first? We are already at 50 minutes mark. Okay, so we build the dictionary. Now this part should not be the final solution, but if this dictionary only has one key, if the length of dictionary keys, if it only has one key, that means we just have that same word in the words list. And what do we need to check then? So when we are checking each word here, if this dictionary only has one key, which means it's the same word again and again, what we do is, instead of checking and decrementing in the dictionary like this, we just now need to check if okay. Yeah, it needs to be moved back out. Yes, so if it only has one key, then the substring we want to check is si until I plus length. Oh wait, so the length of words, that's how many words there are. Length is the length of each word, so that's the entire, so that will be giving us that length of the substring we want to check. So it goes from this start index until start index plus that length of substring. Okay, so that's the substring we want to check. If substring is in S, then result append I. And we can also continue to the next I instead of going through here. Okay, so this little part should take care of that. Oh, keys. Is that not how we get keys? Python dictionary keys. Lowercase. Let's see if this will pass the time limit. Oh, interesting, it gives wrong answer. But it was still slow anyway, so I'm almost sure that this is not the optimal solution. So A, we have AA. Oh, I see. If okay, so the substring here should be AA. So why did it append in S? Then it's 2. Why was that in S? The substring is A. Why is that? I should be 0. 0 plus the length. Length is 1 times how many words there are. That should be 2. So 0 to 2. Oh, I see. I'm getting 0 to 2 from S, and since there are not even 2, okay. If if I plus length times length of words, well, so this is where it should end. If that is exceeding the length, then we can continue. Would be so nice to have it pass within this 1 hour mark though. Okay, let's see. It did run a bit faster though. So still some test cases not passed. Wrong answer. A B A B A B A B A B A B 1 P A P A B A. Oh, I see. P A P A P A. So in this case, we have 3 ABs. So dictionary will just have AB and frequency 3. So length of dictionary is 1, same repetitive inputs, and now the end is gonna be I plus 6. Okay, substring is that substring, so the problem is this substring BA. So we have that substring, it's that substring in S. Oh wait, why am I even doing is, what am I doing here? If substring in S, of course the substring is gonna be in S because we're taking it from S. Wait, what am I missing here? Okay, so the substring I want to check is okay, so right down here we're checking from S and then doing this, so going from S to the dictionary. But if we have just the same words in this case, then we can go from this and go checking S. So the substring we want is actually not taken from S, we want this substring. Interesting mistake. So the substring we want is, since we have exactly the same word, we can do join words. So that should be the substring that we want. Okay. Oh no, we passed the 1 hour mark. Oh, and it's slow, so it's okay. Some improvements, except that we have the same thing wrong. Substring we want. Okay, so we actually still need to check that. A B A B A B B A B A B A. Okay, so the substring I want to check is this one. So substring, I actually want to check if this is equal to S. Okay, we already have end here. So end is start index plus the length times how many words, so that's the length of the substring we're looking for. So from start to end, this should be giving us BABABA. We want to check if this substring ABABAB is equal to that. So, all right. What? Never seen this one before. Output limit exceeded. So it's not time limit exceeded, it's not memory. Output limit exceeded. What does that mean? Is it because I'm printing that substring? Oh my god, it worked. It's extremely inefficient, but it worked. Hmm. What can we do about this? Is this the wrong approach, or can we actually improve on this? Okay. We know for sure that this is not optimal. I mean, we could do something here, but I'm not sure if that's what we should be looking for. So if we do see that the dictionary only has one key, then instead of doing this and then creating the dictionary again and doing all of this again, we could continue for the rest of this just in here, instead of creating that dictionary in each other for loop and also doing this, which all takes unnecessary time and okay, let's just try that. I don't think that's gonna solve the slow runtime here, but let's just put that in there so it's better. So when we find out that we only has that same repeating word, okay, and it's 9. So what do we do when we find that out? And is substring, the substring we're looking for. If substring is equal to this append key, and what else? So after this, return result. Interesting. Okay, I was not expecting that, but apparently that saved us so much time. Okay, that's interesting. Okay, so now instead of doing all the repetitive work, we are just looking, okay, just one key, same repeating in the words, so then we just do this once in here. Substring, drawing words, that's the substring we want to look at. And If and is bigger than that, then we don't actually need to continue because we already know that, okay, the rest of it will be too short. You can just return result. Substring equals k to end. If and, well, yeah, so we return result there. So that should also save us some loops. Oh, it's not working. Oh wait, 0, 0. A 0, 0. Okay, what's happening here? We have this substring that should be A for k in range. So k is just gonna be 0, 0 plus 1, and this 1 and is bigger, and is not bigger. Substring is the same. Oh, because they did not return after that, then they went in here as well. I see. Yes, we want to actually return after this. All right. Okay, same time. Still not very efficient, but much better. Which means there should be better solutions. Okay, let's do time and space complexity for this current solution. Then maybe I would like to think about it for 10 more minutes and see if we have some other ways of approaching this before I look at top solutions, I think. Yeah, so let's do that, and then I will make another video if I do come up with a better solution. Otherwise, I will review top solutions and give a video on just the explanation of the algorithm. All right, let's wrap this up. We have a for loop. Building the dictionary is gonna take linear time, linear with respect to the number of characters. In words. Now this is the special case when we have found out that all other words in words are the same word. So in that case, we know which substring we want to find because it's all the same word, so there's no ordering, there's no permutation in this case. So then we just go through all the substrings in this input S, and then we see if that is a valid one. So this little special case should run in what time complexity? So this will be linear going through all substrings in S. We need to look at all of them. And inside, so this substring, it has a length of, well, potentially 5,000 times 30. So that's the biggest length it could be. So this part is linear to the length of this substring. So this little part should be in the time complexity of the length of S times the length of words, because we are checking all substrings in S, and then we need to check it with words. So if the words have much longer words, then it will take more time to check than if it's a much shorter word. Okay, so next part then. So this is the usual case when we are not considering any special cases. We are putting all the words in a dictionary. We have our start index and start index in S. So we take part of S as the substring we want to check. Start substring, if it is in the dictionary. Oh yeah, it's only checking the same length as the length of all the words as well. So bar foo foo, we just first check bar. Is bar in the dictionary? If it is, we remove it, we decrement. Foo is in the dictionary, bar foo, they're gone. Then another foo that's not in the dictionary, so we have not found it. Then we go on to the next subarray and do the same thing. So what's the time complexity for this then? It will still go the outer linear loop to check all substrings of S. Now inside here, we are doing constant work because we're using a dictionary, and dictionary lookups are constant. That's why we use the dictionary in the first place. So each of this inside this J for loop will be constant time, and then how many J, that's the length of words. Okay, so again, this plus this would be in the time complexity of length of S times length of words. So in total, this solution should have that time complexity, length of S times length of words. And for space, we are using this extra dictionary to store the length. So dictionary would use length of words as space, because we're only storing the words in the dictionary, and we're not using any Okay, so that would also give us same linear length to words. Not really anything else here. Alright, so that's it for time and space complexity. Alright, so I am still pretty glad that I managed to solve it, even though this might not be the optimal solution. I mean, it's obviously not here, but it works, and I'm very much looking forward to checking out the better approaches here, all the smart ideas. I will make another shorter video on this to explain afterwards. I will see you in the next problem tomorrow.